All right, I'm gonna do a real quick video here. This is a Lennox XC21 dash 36. That dash 36 is the capacity. So it's a 36,000 BTU unit. This unit originally had what I believe was an ECM motor. Basically, it's a 2-speed, 825, I believe, RPM low and an 1100 RPM high. And the way that that motor operated was that it had your two legs of your voltage coming in. So you had, your 120A leg and your 120B leg. Or if you're operating on a 208 system, that's a common and 208. Then it had a low voltage 24 common. It had a 24 volt hot that represented your stage 1 and a 24 volt hot that represented your stage 2. And your ground, obviously. So basically that was a 24 volt controlled motor, and it had a little board on it, and what that board would essentially do is control the speed of the motor. It's an electronically commutated motor, an ECM motor. Problem is that ECM motors, especially for this particular model, are quite expensive. It's about $500-600 to replace the motor in this thing. And the ECM motors are slightly more efficient, but it's just not worth it. So what I did is I found a PSC, or a permanent split capacitor motor. A permanent split capacitor motor is very similar in how it's controlled, except that it's controlled on the high voltage side of things. So instead of having your two legs of power coming in and then being controlled by two 24 volt legs with a common, this is being controlled with essentially one common hot wire, and then your other leg, your Bravo leg on the 120 is going to be a high and a low speed. So you have three three high voltage wires, and then your ground. So the way that we're going to replace that ECM motor with a PSC is with a couple of relays. So basically what we have is we have 240 volts coming in to the common terminal of the first relay, and that relay coil is controlled by Y1, our stage 1. The second coil is controlled by Y2, which is our second stage demand, and the 240 volt comes in. The normally closed contact isn't connected to anything, ignore that. The normally open contact goes to the common terminal of the second relay, and then the second relay sends R to our red wire, which is our low speed, and then the normally open position goes to K, which is our high speed. So if you can think about this, when Y1 and Y2 are off, R and K are off, because it's the normally closed position and no power flows. When just Y2 is on, this is sort of an invalid state, because you should never have a condition where only Y2 is on. That means that that should never happen. The thermostat should never be just triggering Y2 and not both Y1 and Y2. So in this case, if just Y2 is on, well, we don't care. Power is still not going to get to it. So both our outputs are off. When just Y1 is on and Y2 is off, this means that we want stage 1 out. So we want just R to be on, and that's the case. So when we kick on Y1, it switches from the normally closed contact to the normally open contact. 240 volt flows through. And I'm writing 240 here. Realistically, this is, the Bravo side of our 240, just one of our legs of 240. And then the other leg is actually connected straight to the motor. But anyway, so 240 flows through, the relay gets switched, it goes to the normally open position, flows to the common position of the second relay, and it goes to the normally closed contact, which is R, so R gets activated, our low speed. And then when Y1 and Y2 are both active, this represents the high speed. 240 volt comes through, still goes to the normally open position, goes to the common, but this time it goes to the normally open contact, which activates K, our black wire. And then we kick on our high speed. And this relay configuration ensures that even if one of the relays gets stuck, gets welded open, gets welded shut, whatever, it doesn't really matter. It can't fail in a state that causes things to go awry. So this is what it looks like on the actual unit. We have our main contactor over here. This yellow wire coming off the top is our Y1. Our Y1 activates this coil of that contactor, and that goes into our first relay right here. I just wanted to clarify real quickly that technically that first relay isn't required. If you're paying attention, technically we could just use the contactor as the first stage and not have to use that relay. And that's technically redundant. You could do this with just one relay to control the Y2, but both options work. Y2 is actually connected to right here on our board. You can see there's Y and there's Y2. So Y2 is this yellow wire right here, and that flows over to our second coil. This black wire underneath is our low voltage common. So that's our common side of the 24 volt AC control. And then this first relay has the red wire, which goes to our A leg of our power. The other side, this white wire, goes straight out to the motor. So one side of the motor is constantly powered and the other side of the motor is switched. And that's how most AC units operate anyway. You can see this contactor is only switching one of the legs of our power. So the output of the first relay is this yellow wire on the top, gets fed into the common of our second relay. And then our second relay has, you can see the red and the black wires output there for our low and our high speed. And that's how it works. Really, really simple. And then this because it's a PSC motor, this gets a little run capacitor as well to be able to get that motor started. But yeah, pretty simple. We're replacing, a $600 solution with like $115 with just a couple of cheap relays and a cheap 2-speed motor. Really simple. Nice way to replace an ECM.